Okay, here's an example involving an accelerating block. So imagine we have a rectangular looking thing which is sitting on the floor like so, and maybe it's contacting the ground only at a couple of points. So let me draw it like that. So maybe let me exaggerate the drawing a little bit. So it's touching the ground only at a couple of points. Okay, and that's the ground. So let's call this point A, let's call this point B, let's call this point C, let's call this point D, and let's call this H. Maybe I'll use a different color. Breadth B, or width and let's say the center of mass is out here, and let's say its height is h over 2. Okay, and it's exactly halfway, let's say w over 2 as well from the endpoint. Okay, so that's a block sitting on a table, or maybe a car sitting on the ground, let's say. And let's say a force is applied. And I'm going to, for simplicity, say that the force is applied horizontally at point A. So a force is applied, F, force applied at point A, okay? So let's set this up. Block A, B, C, D, mass M, height, width are given. Let's say, for simplicity, I mean, if you want to use numbers, you can use these numbers, 1000 kg. Of course, G is 9.81. I'm going to give you the moment of inertia about G. Let's say IG is something like M H square plus W square divided by 12. So all this is given. Okay, all this is given. And you can compute that. And let's say H is 1 meter, W is 2 meters, etc. What else do we need to know? Okay. And then maybe there are two parts. Part A is force F equals F equals, let's say 500 newtons. Okay. And then part B is force F equals 100,000 newtons. Okay, so a relatively small force versus a relatively large force. Okay, let's just try it out for two different force levels. Okay, what are the questions? Compute one I, let's say. I would like us to compute these things for both those situations. So what we will do is essentially derive an expression for the answers, and then we'll plug things in a bit. Okay. So let's compute one, the normal reactions at A and D to the acceleration of point G. Okay. Okay. So these are the things that we would like to compute. Now, what's the first step? The first step is always draw a free body diagram. So let me just draw it like a block. So we had force F like that, and we had the point G. So we have mg acting downward like that, and then we have n a and b like so. Those are the forces. Now, immediately we can write this is point A, point B, point C, point D, point G. Immediately we can write sum of forces equals ma. So do sum of forces equals mag. Always sum of forces on a rigid body or a free body diagram is mass times acceleration of the center of mass. Okay, it does not necessarily give you the acceleration of any other point, but gives you the acceleration of the center of mass. That's very important. So if you say this is the I direction, this is the J direction, then in the I direction we have, let's say the acceleration sideways is ag, and in the vertical direction, let's say it's equal to 0. This is acceleration. No movement vertically, say. Okay. This say is very important. We'll come back to that. This is an assumption that it is not moving vertically, that when you push it horizontally, it does not move vertically is an assumption. We will reflect on that actually when we get to part B. For part A, it turns out that's a good assumption. Okay, so in any case, let's think about it. So for in the I direction, we have essentially F, that's the only horizontal force, equals mag. Very simple. So ag equals F over m. It's like the simplest thing you can imagine. That's part 2, I guess, answer part 2. And what is the normal reaction? What are the normal reactions? The normal reactions, we have Na plus Nb minus Mg equals, well, in the vertical direction, there's no acceleration, let's say, we've assumed, so it's equal to 0. So NA plus NB equals mg. Okay, that's the that's a relationship between actually N and D, I should say, perhaps. Um, okay, if this was a statics problem, Na and Nd would be equal and equal to mg over 2, but this is a dynamics problem, the mass is accelerating. So it turns out that these need not be the same. Okay, so we've already solved for acceleration. We have these two unknowns, normal reactions at A and D. How do we solve for them? Well, we have to use the other equation in rigid body kinetics. We've already used F equals ma. We need to also use sum of moments equals psi alpha. So let's do that. Let's take sum of moments about point G equals I, which is given Ig alpha K. Okay, and if we are assuming that this object is not sort of flipping over or something like that, tipping over, then alpha equals 0. In other words, it's just moving horizontally. If moving horizontally without rotation. So what we have is sum of moments. Let's look at what the moments are. Sum of moments about point G, we have F times h over 2, and that's a anti-clockwise moment, F times h over 2 in the k direction. And then we have ND times W over 2, also anti-clockwise. And we have Na times W over 2, but clockwise, so we put a negative sign. And then the only other force is mg, but mg acts along G, so it doesn't have any moment about G. So and that whole thing is going to be equal to I G alpha K, but if we assume that it's not tipping over in any manner, it's actually equal to 0. And we can then say what we have is F h over 2 plus ND W over 2 plus or minus Na W over 2 equals 0, or simplifying a little bit, ND minus Na equals, well, we can certainly cancel all these 2's. So we have F H over W. Okay, so that's what we have. So that's another equation in terms of ND and W. So let's call this equation number 1. Let's call this equation number 2. And let's call this equation number 3. Okay, so let's use equation number 2 and 3 to derive a relationship for Na and Nd. You can already notice that Na and Nd are not going to be equal to each other. Okay, let's see what we get. So to solve for NA and ND, we can basically add 2 and 3 together. NA will get cancelled. You'll get 2ND equals something. Okay. So add 2 plus 3, we get Na plus Nd plus Nd minus Na equals Mg minus Fh by omega. So 2Nd equals Mg minus Fh divided by W, sorry, not omega. And Nd equals 1 over 2 Mg minus Fh by W. Okay? So that's the normal reaction at point D. And the normal reaction at point A is going to be analogous. So let's call this 4. By the way, this is answer to part 2. We still haven't substituted numbers yet. But to compute NA, let's use equation number 3. Use 3 to get Na equals Nd minus Fh by W, let's say. And that gives us I guess let's actually use equation number 2 instead. It's simpler to use. Which basically says Na plus Nd equals Mg. Nd is already known, so Na plus half Mg minus half Fh by W equals Mg. And then if you bring everything to the right hand side, you're going to get Fh by W plus Mg over 2. So it's basically half Mg plus Fh by W. Okay, so that's Na. Okay, now let's actually, so that's the answer. That's the answer for part 2, more or less. But there's a small subtlety here. Okay. What's the subtlety? Okay, let's actually plug in the numbers to see what the subtlety is. Everything is correct so far. Once you assume that the object moves horizontally, okay, without any rotation, which I think is a reasonable assumption, okay. But we'll examine how reasonable it is in a moment by plugging in numbers. Okay, let's plug in force F equals 500 newtons. So I think we computed. By the way, before we plug in numbers, let's just look at this thing. If there was no sideways force on the object, if you plugged in F equals 0, then you do get Nd equals half Mg and Na equals half Mg, right? And that's actually the statics problem. But now we have a dynamics problem with a horizontal force that's pushing it forward, accelerating it. And because of that acceleration and the horizontal force, we have this extra term. What we find is that the normal reaction at point A is increased, and the normal reaction at point D is decreased by this force, okay? So as you push it forward like so, the normal reaction here is greater than Mg over 2. Normal reaction here is less than Mg over 2. That's what we get. Okay, Okay, now let's plug in numbers. I think we had m equals 1,000 kilograms. G is the usual unfortunate number, 9.81. F, we said for part A, F we said was 500 newtons. H was 1 meter. W was 2 meters. Okay, we can plug everything in. Na is basically half. 1,000 times 9.81 is gonna be 9,810 plus 500 times 1 divided by 2 or something. So half 9,810 plus 250, whatever that is. It's not super important, the actual number. And then ND is basically the same thing. It's going to be minus the same quantity, so it's going to be half 9810 minus 250. Okay, so that's part A, and in newtons, everything is in newtons. These normal reactions are going to be newtons. So that's part A. Okay, so that's a correct answer. This is all correct. This is correct. Now, what about when the force or the horizontal force is really, really large? I think I said 100,000 or something like that. Okay, 100,000 newtons. What happens then? Okay. What happens then? Let's plug things in. F equals 100,000 newtons. Then we have Na equals half, still 9,810, and then plus 100,000, which is 10 power 4 divided by 2, let's say. And that's whatever that is, okay? 9,810 plus 50,000 or something. Okay, you can evaluate that. But ND, that here's where it gets interesting. It's 9,810 minus 50,000. Okay, it's minus 50,000, and you get a negative number. Okay, a negative normal reaction. I'm not particularly interested in the actual number, but the point I want to make is you can compute the number, but the point I want to make is you get a negative normal reaction. Now, what does it mean to say a negative normal reaction? What we've assumed is that, well, what do we mean by normal reaction here? And the sign convention implicit in this free body diagram. What we mean is that if the ground was pushing against the point D, then we get ND is positive, right? So if ND is positive, it means that the ground is pushing on the block. If ND is negative, what does it mean? It means that the ground is pulling on the block, okay, pulling on the block, or the ground is pulling on the car's tires or something, if you imagine these things were tires. Is that possible? The answer is no, right? So you can only push against the ground, but you cannot pull against the ground, because the ground, unless you're wearing shoes with Velcro on the bottom, or some sort of a gum or a sticky substance on the bottom of your shoe, or a sticky substance here, you cannot pull against the ground unless this thing is attached to the ground. If it's not attached to the ground, if it's just touching the ground but not attached to the ground, then you cannot pull on the ground, right? So you cannot have a normal reaction that is negative if you have objects just placed on the ground. So what that means is that this situation, if you have a car or a block that is just sitting on a table, a negative normal reaction is not possible. Um, so in this situation, when the force is really high, what happens is that, like if you assume that this object is moving horizontally with no rotation, you actually get negative normal reaction here, a very large positive normal reaction here. That is actually an indication that well, that the assumption that you made, which is that this object is moving horizontally with no vertical motion, is actually incorrect, because everything follows from that assumption. And so what happens when there's a very large force is, well, imagine you're applying a force, a small force. This normal reaction is large, this normal reaction is small. Keep increasing the force. This normal reaction becomes larger, this normal reaction becomes smaller. You keep increasing it until this normal reaction becomes essentially equal to mg, and this normal reaction essentially becomes equal to 0. So before this becomes negative, it becomes 0. So in this part B, I've given you the force to be so large that it became negative, but for some smaller force, that normal reaction will be actually 0. And if you apply a force that's just equal to the quantity, such that the normal reaction becomes 0, what happens is that this normal reaction will become 0. What normal reaction becoming 0 is allowing that point to essentially take off from the ground. If you essentially provide a much bigger force, what will happen is that this normal reaction will be large. This normal reaction will, well, if you assume that it's going horizontally, will become negative, but what you should assume is that this normal reaction is 0. The lowest it can be is 0. So what will happen is that the object will essentially, if you apply a big force here, will start pivoting about this point. Okay, if you apply a very large force, the whole object, this point will essentially leave contact with the ground. As soon as the normal reaction goes to 0 or negative, this point will leave contact with the ground and then start pivoting about this point. So that you would call a wheelie. You should look that up, YouTube videos. A wheelie is when you have a car or a motorcycle or something, and essentially there's a very, very large force acting on the rear wheels, and what happens is this n goes to 0 and it starts rotating about this point. That's called a wheelie. So when you see a negative normal reaction in such a situation, what you should assume is that, well, it's no longer in the condition of sort of constant horizontal motion. It's actually this normal reaction is becoming 0, and it's pivoting about this point. Okay, so if you actually wanted to solve for what happens when F equals 100,000 newtons, what you would do is part B, redo. Okay, this is NA, ND. ND cannot be negative. ND can at best be 0. So we basically set ND equals 0, and then we say the object pivots about A, and then we can still do so we have AG, we have NA. We have 0 here, and we have the force F here. And then the acceleration state is actually like this, where, sorry, I should have not drawn acceleration here. I should just have drawn the force here, mg. And then the acceleration state is ag like so. In addition, there's an angular acceleration because it's sort of pivoting about that point A. Okay. Previously, we assumed that angular acceleration is 0, but now we do not assume that. When I say pivoting about that point, it's not that that point is fixed in space. It's actually moving forward because the whole thing is accelerating. But essentially, there's an angular acceleration. Is really what I mean. Okay. So what do we have? This allows us to essentially resolve the problem, and we ideally want to use the same equations. Basically, we will say sum of forces equals, in the horizontal direction, equals mag. In the vertical direction, this is along I. In the j direction, unfortunately, this is no longer going to be equal to 0. So this is agx. And then in the y direction, it's actually going to be na minus mg equals magy. And then and then you can do a sum of moments about g equals I alpha, ig alpha k, and that gives us exactly the same as before. Let's actually look at what the fh by 2, ndw by 2, naw by 2, fh by 2 plus ndw by 2, which is 0 because that's what we assumed, naw by 2 equals ig alpha. Okay. So we have another equation number 1, equation number 2, equation number 3. Can we solve for all these unknowns? What are the unknowns? Unknowns are agx, agy, alpha, na. I'll let you think about how to solve these things with these 3 equations.